Welcome to qnawire.
In part A of this problem, we're asked to draw a free body diagram of the stone. We know that the radius of the string is 0.9 meters, the mass of the stone is 0.8 kilograms, and the maximum tension we can have in the string is 16 newtons before it breaks. So if we imagine our stone here, we know there's going to be gravity pulling it down of magnitude m times g. Now it doesn't actually move down because there's going to be a normal force by the table. And then there's also going to be a radial force because of the string. And so I'm assuming that's being whirled around by, say, this point here. And so that's the free body diagram. There's only three forces here, and that completes part A. For part B, we need to find the maximum velocity that we can have before the string breaks. And so for this, we're just going to notice that the radial force is equal to the tension. Now we know the radial acceleration. It's given in the book as v squared over r. And we also know that the radial force is equal to the mass times the radial acceleration. And so it's equal to the mass times the velocity squared over r. And so we can take this expression here and plug it in for the left side here. When we do that, we get that the tension is equal to mv squared over r. Now we can plug in our max tension to figure out what our max velocity is. We also have to plug in our mass and our radius, which are givens in the problem. When we do that, we get 60 newtons is equal to 0.8 kilograms times v squared over 0.9 meters. Now we can solve this for v. And when we do that, we get v is 8.23 meters per second. And that's the final answer.